Hello, Chemistry 10HH students. This is Mrs. Altman. We are on video number 49, Liquids and Solids, Part 4. Here are our objectives for today's video. Pause here. Right, so the heat of fusion, let's say if you have a sample of something that is in its solid form, and then you heat it, and it gets to its melting point, you're going to need to add a little bit more heat to it just to get it to melt. And that amount of heat that you have to add is called the heat of fusion. So there's a certain amount of heat you have to get to add to raise the temperature. And then once it is at the correct temperature, there's a certain quantity of heat that you must add in order to break the intermolecular forces. That is called the heat of fusion. Pause here. And then similarly, you'll have what's called the heat of vaporization. So you take that same sample that we were just talking about before that melted, and then we heat it to its boiling point. And that's a sort of linear heating graph. Once it's at its boiling point, you're going to need to add a certain amount of heat to it. That is called the heat of vaporization. I realize now that that says heat of fusion. That should say heat of vaporization. You'll forgive me. Typically, the heat of vaporization, well, not typically, actually, I can't think of any exceptions to this. The heat of vaporization is always going to be greater than the heat of fusion. The reason why is because with the heat of fusion, you're going from the solid to the liquid phase. So you need to overcome some intermolecular forces. But when you go from the liquid to the gas phase, you need to overcome all intermolecular forces. And therefore, you will need more energy. And then we're actually going to see this visually when we look at heating curves. Pause here. I would just do a rough sketch of the graph. So heating curves, it's a plot of temperature versus heat added, although sometimes we'll just do it as a function of time if we have a steady heat source. These can be used to determine the heat of fusion, the heat of vaporization, and even the specific heat capacity, though we're not going to get into that sort of detail quite this year. So you see that sort of blue plateau, that is due to the heat of fusion. So we heat the ice until it reaches the melting point. We have to add additional heat to get it to actually melt. Then we add heat and we see this linear sort of change. And then it plateaus again, and that's because we need to overcome the heat of vaporization. And then we see another plateau. Or not plateau, another linear increase. Notice how the slopes of these three lines are not the same. That's not super important, but just something that I want to point out. Pause here. So determine the amount of heat sort of mathematically with this. At the plateaus, we use either the heat of fusion or the heat of vaporization. But when we are at a state of matter, say a solid or liquid or gas, we can use the specific heat capacity, which is just how much heat is required to raise 1 gram of a substance by 1 degree Celsius or 1 Kelvin. Elements or compounds with high intermolecular forces will typically have high specific heat capacities. And then you've seen this equation before. We did it in a lab, but whenever we need to calculate quantity of heat, Q, which is just heat in joules, is equal to mass times specific heat capacity times change in temperature. Pause here. All right, I'll work through this on the Google Doc. All right, so there's 2 steps. The first step here is heating the water to the boiling point. To calculate this, we use Q is equal to mCp delta T. So we have 100 grams. We're told the specific heat capacity, which is 4.18 joules per gram degree Celsius. And then by change in temperature, you can assume that the temperature is the max is 100 degrees Celsius. 100 minus 50 is 50.0 degrees Celsius. Put that all in the calculator, and you get 20,900 joules. The second step is overcoming the heat of vaporization. So since the heat of vaporization was given to us as 2.23 kilojoules per gram, we could just multiply that by the number of grams. I don't know why I put that extra 0 there. And so we get 223 kilojoules. So then we just need to add these together, but notice how this is in joules and that is in kilojoules. I'm going to choose to convert the first one to kilojoules, not for any sort of specific reason. I could have just as easily done it the other way around. And then I just add them together. Be mindful of sig figs here, and I end up with 244. Great, thank you so much for watching and have a great night.